Wi-Fi connections? I'm not going to bother. Okay. So they have the same second letter, so you move on to the third letter. And M precedes R, so therefore computer will occur before correspondence in the dictionary. The lexicographic ordering is doing the same, but for numbers. So you take one list of numbers and another list of numbers. By the way, in the dictionary, it doesn't matter the length of the word. Shorter words can precede longer words can precede shorter words, but every word occurs in exactly a unique spot in the dictionary, yes? So these are possibly different lists of numbers of different lengths. Here, just arbitrarily, there are N components, and here there are M components to suggest that these need not be the same length. This could be 5 numbers long, and this could be 12 numbers long. But nevertheless, the lexicographic order proceeds as follows. We'll say that X is lexicographically less than Y if the first number of X is less than the first number of Y. Okay? It's like computer versus light. You compare them on the basis of the first, in this case, number rather than letter. And if this has a smaller first component than this, then you're done. Then don't go any further. You know that this is lexicographically less than this. But if they happen to have the same first number, then you move on to the second number. You put them on the basis of the second number. So another possibility is that they have the same first number, but X2 is less than Y2. If that's the case, then X is lexicographically less than Y, or X precedes Y in the lexicographic order. Okay? But what if they have the same second number? And if they have the same first number and the same second number, then you go on to the third number. And if X3 is less than Y3, then X is lexicographically less than Y. And you continue this until at some point, unless they're the exact same list, they have to differ in at least one component. So at some point, one of them will be lexicographically less than the other. Yes? Questions about that? Okay. Okay, so suppose we have a game, and suppose we have a payoff vector, an imputation for the game V. Okay, so this is an n tuple, an n vector of numbers, specifying the possible payoff or the suggested payoff, we'll say, for each of the n players. Okay? At that recommendation, or at that payoff vector, we would say that the excess of a coalition S at that point is given by this notation. So this is the excess of S at X is given by the difference between the worth of the coalition and the amount the coalition receives according to the payoff vector X, according to the imputation X. Okay? So again, we're looking at a particular point, particular, say, recommendation or suggestion, or someone threw out a possible payoff vector. And this is, in some sense, a measure of how fairly the coalition S is treated at the imputation X. Okay? Now let's look at this for a minute. If this is positive, so this is the aggregate award that the coalition S receives. This is the sum of the payoffs of the members of S at the imputation X. So this is the aggregate payoff that the coalition S receives at that imputation. If this is greater than that, if this is positive, it means that the coalition S can do better on its own than at the imputation X. Right? It means the worth of that coalition is greater than the amount it receives at X. So if it's positive, it means that the coalition S is sort of getting shortchanged. They're getting less, at least according to them, they're getting less than they deserve, or less than they could get on their own. So it's not really, well, they would object to this imputation. Okay? They might say that, no, we're not going to accept that because we could do better on our own. So if this is positive, it's a measure of how badly the coalition S is treated at the imputation X. Okay? Conversely, if this is negative, it means that the coalition S is being offered more than it could achieve on its own. Right? So the more negative this is, the more favorable the imputation is for the coalition S. And what they would really like is if they were awarded the entire amount, then this would be as negative as possible. Yes. Okay, so positive values represent, you might think of these as valid objections. The coalition S, if this is positive, the coalition S could object to this. And the more positive it is, the more shortchanged it is, the worse it's treated, the stronger its objection to this as the solution to the game. Okay? So that's basically what I've said here. If this is positive, it specifies how much better S can do on its own. And the larger this is, the stronger the coalition's objection to this particular recommendation, okay, or this particular suggestion. If this is negative, then the absolute value of this represents how a surplus to the coalition is, how much better off they are at this than they would be on their own. Okay. So that's going to be important because in some sense, the nucleolus is going to focus on the excesses, how much either better off a coalition would be on their own to these valid objections or the amount of surplus they receive. Okay? So at an imputation X, this notation is going to list out all the possible excesses for each coalition. So there are a lot of coalitions. I mean, if you have a 3-player game, then there are 3 times 2 times 1 coalitions. Okay? Wait, is that right? 3 times 2 times 1, yes. That's not true. If you're a 3-player game, then the number of coalitions are this. In fact, in general, this is the formula for the number of non-empty coalitions. So if you have 3 players, there are 7 possible coalitions. There are the coalitions 1, 2, 3. There are the coalitions 1, 2, 1, 3, 2, 3. And there's the coalition N. So this is just intended to represent, each of the possible coalitions. But what we're going to do is we're going to list out, consider every coalition, and we're going to see what their objection is, what their excess is to this particular recommendation for that coalition. So this is the excess of coalition S1 at X, the excess of coalition S2 of X, and we're going to list out all 2 to the n minus 1 of these excesses. Okay, then what I want to focus on is look at this list and rearrange them from highest to lowest. Okay? So this notation, theta of X, it's a little bit, this is the notation we defined before. E of X lists all of these numbers. Theta E of X is then going to rearrange those from highest to lowest. But I'm going to abbreviate that because there's no reason to carry that E around. So theta of X is the ordered vector or list of excesses in decreasing or non-increasing order. Okay. So the nucleolus of V, again, we're going to look at an example in a minute, so I just want to go through the definitions first. The nucleolus of V is the imputation, so it's the X such that this ordered vector of excesses is lexicographically less than at any other imputation. So you could think of this as follows. These are, in spite of the fact that some of these might be negative, which is good for the coalition, but in general, let's think of these as the objections to the recommended solution X by all of the different coalitions. Okay? Sometimes the objection, quote unquote, might be negative. Mm-hmm. So what the nucleolus is going to do is it's going to go from the highest objection to the lowest objection. The presumption being that the higher the number, the stronger or the more valid the objection of that coalition to that suggested outcome. And the nucleolus is going to try to lexicographically minimize. It's going to try to minimize the maximal objection to X. Okay? Let's try that one more time. The nucleolus will try to minimize the maximal objection to X. It will pick the X that minimizes the maximal objection. So again, these are the objections by all of the coalitions. We're going to arrange these from highest to lowest. The presumption is that the highest has the most valid or legitimate complaint against X, and we're going to try to tamp down or minimize these legitimate complaints as far as we possibly can, or tamp down the complaints starting from the most legitimate, going all the way to the least legitimate. And we're going to try to tamp them down or minimize those from top to bottom, from greatest to least. Okay, so this minimizes the maximal objection. Okay, these are the properties of the nucleus, but let's first look at some examples. Okay, this was the first example of a game, of a two-player game that we considered a couple times ago.